Okay, guys. A very good morning to all of you. Okay, today we are going to discuss about the abrasive machining, abrasive jet machining. Aman, please let me know whether the screen is visible.
Yes, sir, it's visible.
Okay, thank you. Guys, yesterday in the last class we started the abrasive jet machining, and yesterday we discussed about the principal part that how the abrasive jet that we are using, means what's the exact meaning of the abrasive jet. Okay, and how the principle is that we are maintaining the air or any gas at very high pressure in the range of 2 to 10 bar, and then uh, this air or the pressurized air or the pressurized gas is passes through the hoses and mixed into the mixture along with in the abrasive particles, okay, or abrasive grids we can say. So that will mix along with that and they will make a very high velocity, means abrasive particles or the abrasive grids retain the very high velocity, okay, or gain the very high velocity, and they impinge over the workpiece surface, okay. So this is how when they impinge over the workpiece surface they will remove the material, okay. So that we have discussed. Also, like principal working and the material removal rate, up to that we had discussed yesterday. Okay, and we also discuss about the process parameters. There are four process parameters, that is abrasive particles, carrier gas, abrasive jet that we are using in the nozzle. So that we have already discussed in the detail yesterday. And we also discuss about that if there are two types of the materials, generally it is applicable for all kind of materials. But if we categorize them, then it should be in a two categories, ductile and the brittle. So this process, abrasive jet machining, is applicable for both. Okay, ductile and the brittle, and how the what is the mechanism of material removal and how exactly the material is removed during these two materials these during these two materials when we are using, that we have gone through yesterday. Okay, guys. So today I'm just going for the modeling of the material removal rate. Okay, guys. So I expect that yesterday whatever we have discussed it's clear to you guys, but still if you have any doubt you can ask me later on as well along with this today's class. Okay, so let's start. Okay, so yesterday we had discussed up to this one that this is a this is the abrasive grid, because generally the size of the abrasive particle here we are defining in terms of the grid. Okay, so if we are defining the size, then generally it is defined by the diameter of the grid. So this is basically we considered yesterday that this is dg. Okay, that g is basically the grid and d is the diameter. Okay, so this is the diameter of the grid. Now first of all, we have to going to modeling the material removal rate. So for the material removal rate it will be like different for the ductile material and it will be different for the brittle. Reason is, yesterday we had discussed that when we are talking about the brittle material, that time it will become the semi sphere in nature. It's exactly not that much in size what the figure is mentioned, but very small, because the size of the abrasive particles that we are using, that is in the range of 10 to 15 micron 50 sorry 50 microns. Okay, so when it will impinge over the workpiece surface it will remove a very small quantity of the material, but we are just assuming that that should be in a semi sphere form. Okay, maximum that can be written. So for the brittle material, this is the material removed in a semi sphere, and for the ductile it is different. So what the volume will be, okay, what the volume will be, that yesterday we have discussed about this one as well, like initially it is this grid is impinging over this surface over the workpiece. Okay, and like here, and then it is indenting inside. Okay, then we discussed that this is the radius, this is small r is the radius, and this, if this is a hemisphere, then this will be small r throughout. Okay, throughout means from here to here, as well as when you will see from the top view, this will top view will also be visible, looks like this one. Okay, this is a circle from the top view. Okay, it's not a sphere, sorry, ellipse. Okay, so from you will see from the top view it will be a circle. Okay, guys, so this is a semicircle. So let's discuss first for the brittle. Okay, so when we are talking about the brittle material, then the volume of the material which is removed, okay, how much amount of the volume is removed when one abrasive particle will impinge over the workpiece surface. So for that it will be equals to 2 by 3 because it's a semi-sphere, so it's 2 by 3 pi r cube. Okay, this is equation number 1. And if we are talking about the brittle material, then this sorry, ductile material, then for that yesterday we discussed that this one, this it will be like a circle from the top when you will see, but when you will talk about this portion, the below portion which is inside from which the workpiece has been removed, it will not be exactly like this, it will be like this one. Okay, it will be like this one. So exactly we cannot say that whatever the radius initially that we maintaining, that is a delta, because yesterday I discussed that this is the maximum indentation that can be formed when the abrasive grit is impinged over the workpiece surface. So when some amount of the material is still shocked or stored by the workpiece, then definitely only exactly the when the impingement was there, the impingement was up to this line. Okay, but in case of ductile, it restore that energy. So this much amount of the material on which the effect actually was there, but it is not removed from the workpiece area. Only this much amount of the material is removed from the workpiece area. So exactly we cannot say that this complete radius will be the delta. But when you will see from the top view, it will be looks like a circle, it will be looks like a circle. Okay, so we have to find out the volume. So can we say that this is the area? Now area into height. Okay, so this is the area, and if we are talking about the height, then height we are considering that this one. Okay, or exactly we cannot say because it's not a cylinder, so that we can say that this area into height, so that will give you the volume. But for this, the we are writing this equation that volume as like pi into delta square, okay, into dg by 2, dg by 2 minus delta by 3. This equation is we get it from the heat and trial method. Okay guys, means by the experiment, and on the basis of that experiment, heat and trial methods, so that we gained in some of the books. This if you will see, then this equation is directly written as pi into delta square into dg by 2. Okay, so this also can be you can write, but actually this equation was this one. But here, like, what is delta is basically the indentation, and you are taking just one third of that, and after taking one third, you are just comparing the radius of the grid size. Okay, so that will be very small. Okay, so that's why this delta by 3 here is negligible. So this equation can be written as pi into delta square into dg by 2. Okay, so this is the volume. Now we are going to calculate the material removal rate. But if you will see in this equation, then in when we talk about the brittle material, then this equation in terms of small r, that is the radius. Okay, and if we talk about this one, then this equation in the form of delta or dg is nothing but like r. We are dg here means r is the radius and dg is the diameter. But please do not confuse, this radius is different, it is not half of the dg by 2. Okay guys, dg is the diameter of the grid and the radius is this one. It's not like this radius we are talking about. Okay, it's not like that. It's the radius of that, how much impingement is there on the basis of that circle is formed. Okay, that semi-sphere is formed, it is basically the radius of that. So please do not confuse. Now what we are going to do is, we have to keep both the equation in same, means we have to write this both the volume in the same, like either in delta or in the r. So what we have to do, we have to find out the relationship between r and delta. So first of all we are doing that, then we will go for the material removal rate. Okay, so guys, today this complete session is based on the this theory of this that material removal rate, because we are modeling the material removal rate. Okay guys, so there is no theoretical portion, only this mathematical approach is there. Okay, so if you have any doubt, you can just ask me. Okay guys, so now, okay, so what we have to do next, we have to find out the relationship between small r and delta. Small r is basically the radius, and the delta is basically the indentation. So for that, what we are doing is I'm just removing this one. For this, this is I'm considering this triangle, means if we are taking this one, OA is basically the radius of this grid. So radius is like in terms of diameter, it will be dg by 2. Okay, And if we talk about this one, this BC, so this will be like the indentation. Okay, so this is indentation, that is delta. Okay guys, now if we talk about this OC, then it is also the radius of this grid. So this is also this is from here to here, this is also dg by 2. Okay, so now we are talking about the triangle A, B and O. A, B and O, because this is 90 degree, and I'm using the Pythagoras rule. So Pythagoras rule is what? That hypotenuse square, that is AB AO square equal to base square plus perpendicular square. So this is the base, that is AB plus OB square. Okay, so this will be equals to like AO square equals to AB square plus OB square. Okay guys, this is the Pythagoras rule, because this is the 90 degree. Okay, so AO is dg by 2, so this is dg by 2 whole square equals to AB is how much? This one. Okay, and this much is how much? This is small r, this much is small r. Okay, so this is small r square plus OB is this much. Okay, from here to here. So how we calculate this one? OC is dg by 2 and this is delta. OC is dg by 2 from here to here, and BC is delta. So this will be equals to dg by 2 minus delta. Okay, so this is dg by 2 minus delta square. So just open it. So this will be like dg square by 4 equals to r square plus dg square by 4 plus delta square minus 2 into first a into b, it's a minus b whole square. Okay, so this is dg by 2 into delta. So this will be cancel out, this will be like cancel out from both the side. So what is remaining in the left side? That is 0. In the right hand side, this is r square plus delta square minus dg into delta. Now guys, here it's delta is there, so I'm just eliminating this term. Reason is delta is very small. By the way, delta is initiated by the abrasive particle, and abrasive particle has a size in micron. So this indentation, that is less than 1, we can say, that is that the value is in points, and when you will square it, it will again become less. Okay, and multiply with someone, it will become less. So we are just eliminating this one. So if we are eliminating, so from this equation we can get like r square will be equals to dg into delta, and from here r will be equals to root square dg into delta. So this is the relationship between the r and delta. Okay guys, so this is equation number, this was equation number 1, this was equation number 2, and now I'm keeping this one as a equation number 3. So what we have to do now, this is r is here, so either we can convert this complete VB in terms of the delta, or we can put this delta value over here in terms of the r. But guys, please listen that here r, what I said in the beginning, that we are considering that this the material, the volume that is removed for when we are considering one abrasive particle in consideration. Okay, so if there are different types of the particles, it has a different diameter, impingement velocity is same, the force is same. Okay, because that is coming with very high pressure, and pressure energy is converted into the kinetic energy. So the impingement force is same. So if it is same, and when it is of different diameters, then definitely it has the different indentation as well as the different radius. Okay, so what we can do is, I am just keeping all the value in the delta form only. Okay, so what I'm doing is, I'm just converting this r in terms of delta. Okay, now why I'm converting, I will tell you later on as well. Okay, so for the time being, just consider that we are converting this VB in terms of delta. Okay, so let's go to the next page. Now VB equals to this is 2 by 3 into pi r cube, 2 by 3 into pi r cube. So, and I'm just keeping this r value over here. So this will become 2 pi by 3 into, this is dg into delta raised to 3 by 2. Okay, because it's a square root, 1 by 2, dg into delta is raised to 1 by 2. So when you will take it cube, it will become 3 by 2. Okay, and this volume will be like VD will be same, because this is equation number, like you can keep it 4. Okay, and equation number 5, that will be equals to VD equals to pi into delta into dg, pi into delta square upon into dg by 2. So this is equation number 5. Okay, guys. So now both the equation is converted into the delta form. Okay, delta and the dg form. Now we are going to calculate the material removal rate. Okay, guys. But again, because when we calculate the material removal rate, if we'll calculate right now, okay, then we can get that value in terms of delta. Okay, in terms of delta. And the same thing what I told you in the past here, that we have to convert both these volume in the same term. Means either you should keep in r or on delta. But when we are considering that there is a different size of the particle impinge over the workpiece surface, then definitely r will also be different and delta will also be different, because initially what we considered, this delta is basically the maximum value. This delta is basically the maximum value. So if the size is large, then this delta will become less. Okay, that concept we will discuss later on. But if the size is large, then this indentation is less. So what we are going to do is here, before calculating the material removal rate, I just want to remove this delta from here. I just want to remove this delta from the here, and I just want to keep it that what the values is will be given to us. Okay, means values means मान लीजिए कि we are considering the abrasive particles. So abrasive particle, when it will impinge over the workpiece surface, definitely there will be indentation. But this is a value that we have to find out. But what I'm doing is what the value is available to us. Available क्या हो सकता है? आपको ये दिया हो सकता है कि like how much kg of abrasive particles we are using. When we are using the abrasive particles of alumina or silicon carbide or dolomite or glass beads, then we know the strength of these abrasive particles. So in terms of that what properties is known to us or what properties we can calculate, in terms of that I'm calculating. I'm just converting this one. Okay, guys. So please do not confuse. Okay, I will brief you later on as well. So what I'm going to do is here we are considering two things. First, okay, let's move to this one, that is kinetic energy and the work done. So two things. First is we are going to discuss about the kinetic energy. Okay, so kinetic energy, how we can write the kinetic energy? Kinetic energy will be equals to half m into v square. Okay, so m is basically the mass and v is basically the velocity. So mass is of what? Here the pressure energy is converted into the kinetic energy, but this kinetic energy is retained by what? This is retained by the abrasive particles, because abrasive particles is only moving with a very high velocity, and because of that only the material is removed. So this mass will be of grit, so this is mg, please keep in mind. Okay, and the velocity, that is v square. Okay, guys. So now this is the kinetic energy, that is half mg into v square. But here I'm just converting this mass, because that is not the property. Property is the density. Okay, so I'm just converting this into the density term. So when you will write that mg, that is mass of the grid or any mass in terms of the density, that will be equals to rho g into volume. Okay, into volume. Okay, so volume will be how much? Volume, if we are considering, simply considering, then there will be a semi sphere, then this will be equals to rho g into 2 by 3 pi r cube. And in terms of, okay, sorry, we are considering this volume will be not this volume will be of the grid. This volume will be of the grid. Otherwise if you will consider that 2 by 3 pi r cube, then it will be like if you will consider this is 2 by 3 pi r cube, then this will be like you can say like this can be only for the ductile brittle material. So we cannot apply this kinetic energy through the ductile material. So that's why please keep in mind this volume is not that much. Okay, this volume is not this one. Volume will be for the grid. Now how we calculate the volume for the grid diameter is given to you. Okay, so in this is a sphere in nature that we have already discussed in the assumption part. So this will be equals to 4 pi into r cube in terms of radius. Okay, or in terms of, if I will convert the diameter, then this can be written as like pi dg cube upon 6. Okay, when you will convert this one, so I'm just writing directly, guys. So this will be into pi into dg cube upon 6. So this is the mass. So this is pi into rho g into dg cube upon 6. Okay, so this is the mass, so I'm just putting this value over here. Okay, over here, so this kinetic energy will be equals to half, that is 1 by 2 and 6, that will become 1 by 12 pi into rho g into dg cube into small v square. Guys, please consider this is small v. Okay, that is the velocity, not the volume. Okay, please do not confuse. This is small dg square into small v square. So this is the kinetic energy. Okay, now this equation number, okay, this equation will become number 6. Okay guys, now this is the kinetic energy. Next will be the work done. What is the meaning of work done? Work done is like how much force is applied up to some specific displacement or length, distance we can say. Okay, so if force, that is the work done. Okay, sorry, force, work done, that is work done will be equals to W into force, that is now here the force, this force is impinging over the workpiece surface. What is impinging? The abrasive particles or abrasive grids. So this force is basically of the abrasive grid, that is Fg, into how much distance that is traveled. This distance is traveled when it will impact it initially this area at this surface. Then this much maximum we are considering that this is traveled by delta. So the distance is delta. So this is Fg into delta. Now this Fg is basically the force, but I do not want to consider this force here. Means I do not want to take this value move further. Okay, but so what can I do is I can replace this value. Okay, how I can replace that? Force is equals to how much amount of the strength of these abrasive particles which is impinging over the workpiece surface, upon when it is impinging over the workpiece surface, how much area is covered by that. Means simply if I say, then that will be equals to pressure into area or strength into area, because here we are considering the strength part. Okay, so if this is the strength, then this will be equals to area into strength of the abrasive particles. Okay guys, this is the area into strength particle. So this is in meter square and strength will be in Newton per meter square. So Newton will be there, means force will be there. Okay, so if I am writing this area, then this area will be equals to, in terms of delta I am writing, because here I am writing in terms of delta because the work done that is covered by that. Okay, so this work done will be equals to pi into delta square. Sorry guys, this is in terms of r only. Okay, sorry, this is small r square into this is the area, that is pi into r square from the top view, because cross sectional area we always consider, and into strength. So strength I am considering either we can represent by the sigma, but here in standard book it is mentioned that h. So h is nothing but the hardness we are considering, because we are considering that because of the brittle fracture only the material is removed. Okay, so at that time we consider the hardness, so that's why we are writing h by h. Okay, into delta. Now guys, here I just want to discuss one more concept. If we are talking about the ductile material, brittle for okay, but if we are talking about the ductile material, then like it should be that indentation will be like this. Okay, indentation will be like this. So exactly we, if we consider this length, then this length will be different, 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 and at every periphery, in that case of the ductile material, this delta will be different. So what we have to do is, what we have to consider, we cannot consider a significant value, means delta we cannot write. So what we have to do is, we are writing just the average value of that, that we will take the delta 1 plus delta 2 plus delta 3 up to that, and the average we will consider. Okay, so this will be like 1 by 2 into pi into r square into h into delta. I did not write this half in the beginning, because I do not want that you should go for a there will be any confusion. Okay, so this is equation number 7. This is the work done by the abrasive grit on the workpiece surface. Okay guys, so now from here, yesterday we discussed about this point. Okay, and I told you that I will discuss in the later on. So this is the point, that kinetic energy of the particle is fully utilized in the removing material. What is the meaning of that? When this abrasive particle will impinge over the workpiece surface, and that will impinge means it will move inside means work done. Okay, means whatever the kinetic energy, that is completely converted into the work done, means there is a no loss. We are considering these assumptions that there will be a no loss. Okay, so if there is a no loss and this kinetic energy is fully utilized to remove the material, then fully utilized means the work done. It means the kinetic energy will be equals to the work done, means this kinetic energy will be equals to the work done. So just from the equation number 6 and 7, just write it like 1 by 12 into pi into rho g into dg cube into small v square, that will be equals to 1 by 2 into pi into small r square into h into delta. Okay, so this pi will be cancel out, this will become 6. Okay, and what else we can do? We can do one more thing here, that is we can replace this one. Okay, this r, this we have already calculated from the equation number 3, that will be equals to dg into delta raised to 1 by 2. Okay, so just replace this value. So when we will replace it, it will become like in the right hand side like rho g, sorry, this will become 6 rho g into dg cube into small v square upon 6 equals to r, that will be equals to dg into delta, this is square, so this will just become 1. Okay, into h into delta. Okay guys, so this is dg and this is dg cube, so it will become a square. Okay, and this is delta into delta, so this will become delta square. Okay, so in this right hand side, this will be h into delta square. So from this equation you can just calculate the value of delta. Okay, so if you will calculate the value of delta, first calculate the value of delta square, so it will be like rho g into dg square into v square upon 6 into h which is here. I'm just reciprocating. Okay, so from here the delta will be equals to this is dg into v into rho g upon 6h raised to 1 by 2. Okay guys, so this is the value of delta. Now if just look at here, that this dg is basically the diameter. Okay, that is the diameter. Okay, so this is the abrasive grid property. Okay, that how much size we are taking. What is the velocity, that is again depends that how much pressure we are using. Okay, how much pressure we are using, and the pressure energy only converted into the kinetic energy. So from that we can calculate the v value. Rho g, that is the grid property. Okay, means density of the grid. Okay, h is basically the strength. So now again the strength of the abrasive particle, so that is also the abrasive particle property or the grid property. So now you can replace this delta value with respect to this formula into the volume that we have calculated. But Zibran, where are you? So, what we can do is either here we can replace this delta value, this volume from this volume. Okay, and we can just convert that into the dg, or recently what we have calculated, that is in terms of v, rho g and h. Okay, so here I'm not just putting that value. I will we will put this value later on. So now we are going to calculate the material removal rate. Okay guys, so okay, so first of all, the material removal rate for the brittle. So MRR in case of the brittle, that will be equals to VB, that is volume of the brittle material that is removed during the brittle material, into number of abrasive particles, number of abrasive grids. Okay, let's write number of abrasive grids impacting per unit time or per unit second. Okay guys, so now this is the VB, that is the volume, how much amount of the volume is removed into the, like, what is material removal rate? Material removal rate is how much amount of the material removed per unit time. Okay, so this is how we can calculate this number of abrasive particles or the grids impinging over the workpiece surface per unit time. That is what is the flow rate and what is the mass of that. What is the flow rate, that mass flow rate, upon what is the actual mass of that abrasive particle. Okay, so just I'm writing, this is, sorry, this is VB into how much mass flow rate, that is m dot g, upon what is the mass of that, that is mg. Okay, so mg is again like from here. Okay, here we have calculated this mg, so this mg will be equals to pi by 6, this one, pi by 6 into rho g into dg cube. Okay, so just I am replacing this value, so this will be equals to vb into m dot g upon pi by 6 into rho g into dg cube. Okay guys, now just replace this value, this vb, now you can put this value, that is of vb. So from vb is equals to 2 by 3 pi into dg into delta raised to 3 by 2. So this is 2 by 3 pi into, this is dg into delta raised to 3 by 2 into m dot g upon pi by 6 into rho g into dg cube. Okay guys, so from here like pi, so this pi will be cancel out, and this 6, like here it's 3, it will become 2, so it will become 4. Just I'm just writing, that is m dot g into dg raised to 3 by 2 into delta raised to 3 by 2 upon rho g into dg cube. Okay, so this is cube and this is 3 by 2, so when you will bring it downside, it will become 3 minus 3 by 2. So when you will take this LCM, it will become again 3 by 2. Okay, so you can simply write this will be equals to 4 into m dot g into delta raised to 3 by 2 upon rho g into dg raised to 3 by 2. Guys, please check if there is any mistake by my side, please let me know. Okay, so this is the material removal rate, material removal rate during the brittle material, for the brittle material. Okay, so this is like this is the material removal rate, that is depends on mg, rho g, dg and the delta. But as I said in the beginning, that two things I said. First is that we are calculating this material removal rate when there is a single abrasive particle is impinging over the workpiece surface. It means that when two particle will impinge, three particle will impinge, or number of particle will impinge, this material removal rate will be different, because every particle will impinge and that will they will remove the material. Second, when this different diameters particles is impinging over the workpiece surface, this r and delta will be different. But here, by the way, there is no value of r, but delta is there. So what we have to do, we have to replace the value of delta. Guys, that's why we calculated this value. आपको उस टाइम पे शायद समझ में नहीं आ रहा होगा, बट अब हम उसको कैलकुलेट कर सकते थे, बट अगर हम उसको अब right now we are going to calculate this one, so there will be a confusion. Okay guys, so please like this was the equation number 8, so this is just keep it, this is equation number 9, and from that value, that delta, from this 8 equation you can just replace this value. So when you will replace it, so this will become mrr, that will be equals to 4 into m dot g into rho g into dg raised to 3 by 2. Okay, now this will be like, just put the value of delta. So when you will put this delta, this will be like dg into v into rho g by 6h into 1 by 2 raised to 3 by 2. So just multiply this 3 by 2 inside. So when you will multiply, it will become 4 into m dot g upon rho g into dg raised to 3 by 2. Now when you will just take it inside, so this will be like dg raised to 3 by 2, v raised to 3 by 2, and it will become like rho g upon 6h raised to, it will become 1 by 2 into 3 by 2, so this will become 3 by 4. Okay guys, now here this term and this term will be eliminated because both are same. Okay, now what you can do is I just simply writing this is v square. Okay, so I'm just writing this equation will be like 4 into m dot g upon rho g, okay, into uh, rho g, sorry guys, here also like here rho g is there, and this is power 3 by this is 3 by 4, so like 1 minus 3 by 4. So when you will bring it downside, so it will become 1 by 4. Okay, so this is like uh, okay, this is 4 into m dot g into v square upon rho g raised to 1 by 4 into 6h raised to 3 by 4. Okay guys, either you can write this one, or if I simply write in a simplified form, then this equation can be written in terms of like, sorry, this is 3 by 2. Okay, so this equation you can write like uh, 4 into m dot g. Okay, let's do not simplify it. But the meaning I want to say over here is why I was trying to simplify, because as I said in the beginning here, that first one here, the first point, that is this material removal rate is calculated for one abrasive particle. Okay, it means that for second, if two particles will be there, then it will be different, then three, then it will be different, and it will be different not only when the number is increases, but when as particle will be different, the diameter of that will be different. Okay, so diameter will be different, so this material removal rate will also be different. So just I'm just writing that simply, like material removal rate will be approximately, which is proportional to, we can say like here, because this number can be vary. When there will be a 2 material removal rate, it will be different, 3 it will be different, but overall we can say that material removal rate is depends on mg v raised to 3 by 2 upon rho g raised to 1 by 4 and h raised to 3 by 4. This material removal rate for the brittle material, it depends on mg into v into rho g in and h. How it depends? This is by this relation. Okay guys, so please remember this one. Okay, and just write it into somewhere, because many problems has been asked, okay, in many of the examinations. Please keep in mind this one. Okay, now this is for the brittle, and this is equation number 10. Similarly, we have to go for the ductile material. Okay, guys. So this is our last that we are just going for the ductile material. Then we will finish this lecture. Okay. So let's go for the ductile material. For the ductile material, material removal rate for the ductile material will be equals to, the material removal rate is same, how much amount of the volume is removed per unit time. Okay, so this will be like volume during the ductile material, sorry, ductile material into Vd into m dot g upon mg. Okay, so this is simply you can write this is Vd, how much the value of Vd, this is pi into delta square into dg by 2. So this is pi into delta square into dg by 2 into m dot g upon, this is pi by how much, this is pi by 6. Okay, pi by 6 into rho g into dg cube. Okay guys, so here pi will be cancelled out, it will become 3. This dg will also be cancelled out, so it will become a square, so this formula will become 3 will go upside, so this is 3 into m dot g into delta square upon rho g into dg square. So this is in terms of the delta. Okay, so this is equation number 11. So now, but we have to replace this delta, so just we have the value, that is material removal rate during the ductile material will be equals to 3 into m dot g upon rho g into dg square into, now we are replacing this delta, so this delta will be equals to dg into v, dg into v into rho g upon 6h raised to 1 by 2 into power square. Okay, so just simplify this one, this is 3 m dot g upon rho g into dg square into v square into rho g, because this is 1 by 2, so this will be cancelled out, so this will become rho g into 6h. Okay, now dg square will be cancelled out, rho g will be cancelled out, and when you will see this one, now nothing we can remove, this one also like 1 by 2. Okay, so this material removal rate in case of the ductile, that will be equals to 1 by 2 into m dot g into v square upon h. And as I said that this is for one and one abrasive particle, so this number will be changed. Okay, so overall if we say that this material removal rate for the ductile material is proportional to the mass flow rate of the grid particles into the velocity square upon h, the strength of the abrasive particles. Okay, so this is in case of the brittle ductile material. Okay guys, so Please keep in mind these two formula, and also keep in mind that here if you will see this equation for the ductile material, this depends on the three things: m dot g, that is mass flow rate, velocity, and the hardness, or strength we can say. Here the mass flow rate, velocity, and the h, which is same as the ductile, for the ductile, but it is different. This one is different, okay? This rho g, okay? That during the brittle material, the material involved rate is not depend on the rho g, but in case of the ductile brittle material, it depends on rho g. Okay, guys. So it is for four things, and there is three things. Guys, I'm giving you 1 minute. If you have any doubt, you can ask me. Okay, and one more thing, like I'm sure that there will be a lot of doubts. Okay, because this is completely the mathematical derivation. Okay, and mathematical derivation. So you, if you want to do it in a better way, if you want to understand it in a proper way, then you also have to go in this way. Means एक बार आपको try करना पड़ेगा घर पे. You have to write it in your notebook and then go through this one by one steps, follow the steps, then you proceed for this one. Okay, so then only you will get to know exact thing that what is happening there. Okay, so if you have any doubt still, you can ask me. Okay, guys, if you do not have any doubt, then I'm just stopping this recording.